Okay, in today's lecture, we'll study or we'll try to draw the SFD and BMD for a simply supported beam, which is uniformly distributed load over its entire length, right? So we have a beam which is simply supported, and we have UDL along its entire length. So let's draw the figure first. Let's assume that there is a beam which is simply supported at the two ends. So we have reactions at both the ends, A and B. So we have reaction RA at end A, B, and then we have a uniformly distributed load along its entire length. Now let's say that the intensity is W per unit run, and let's say that the length of this beam is L. Okay, so this is the case. Now again, this is simply supported beam having uniformly distributed load over tire length. So this is the case that we are discussing as of now. Now again we need to find out the reactions. Find the reactions, and in order to do that we'll apply the equilibrium conditions. Moment about point A is equal to 0. So before we do that, I'll draw the FBD or the free body diagram for this particular case. Now if I have to find out the reactions, then I need to replace this UDL with a point load, right? And we know that, so the intensity of the UDL will be W into L, because W is the intensity multiplied by its length will give us the load. So it is WL, this is the point load, and it will act at a distance of L by 2. Now this will be L by 2, right? So if you look at the problem now, this problem has been converted into a specific problem, which was the one which we had for the point loads. But the only difference is that over here we have the load distributed over the entire length, right? So first we'll find out the value of RA and RB. In order to do that, we have taken the moment about point A is equal to 0. So what I have is I had W into L into L by 2. Now this is clockwise, so I'm taking this as positive, minus RB into L is equal to 0, right? So from here I get RB is equal to L will cancel out, I'll get W into L by 2, right? Now from the second equilibrium condition, sum of all the forces in the vertical is equal to 0. I know that RA plus RB is minus WL is equal to 0, or RA is equal to WL minus WL by 2. So I get WL by 2 again from here. So from here it's clear that the value of RA and RB is same, and the value is WL by 2. So if I draw it, it should look something like this, that the value of RA is WL by 2, the value is WL by 2, the distance of L by 2 from either end, we have WL. Now if you go back and have a look at the simply supported beam which had a point load at the center, you'll find out that the reactions at the end were half of the point load. So same as the case over here. So we have that, right? Now for SFD, for shear force diagram, now for the shear force diagram, what we'll do is we'll take a section. Okay, so let's take a section between B and C, section between point B and point C, right? Now C is the midpoint, so I'm taking, this is C, somewhere in between, so we take a section over here. Let's say this is X, so this distance is X basically, right? So if this distance is X, what will be the shear force? So shear force at X will be what? How much? Shear force should be how much? It should be the RB. RB is what? RB is C, W L by 2. Now this is acting upwards, right? This is acting upwards, minus W into X, now whatever the X is, right? Now if we put the end conditions at point B, at point B X is equal to 0, right? If X is equal to 0, then shear force at point B is equal to WL by 2, right? So at point B, this is WL by 2. Now this is positive, it means it is upwards. Now if it is upwards, that means that the shear force diagram will be negative. SFD will be negative, right? Now let's come to point C. Again I'll do this twice, once with this equation and once when we take a section beyond point C and beyond, between point A, right? So at C, the value of X is L by 2, right? So shear force at point C should be equal to, so it is WL by 2, so this is WL by 2 minus WL by 2, so this is equal to 0. So at point C we see that the value comes out to be 0, right? Now I'll change the page and then we shall continue. So what we have as of now is we have that at point now. So this, I'll draw the schematic again. Sure. So this is RA, this is RB, and this was B. W, right? Now let's say this point somewhere here we have C, which is the midpoint, right? And now let's take the section over here. So this is A, this is B, and this is C, and this is X. Now let's say that the distance from point B is X, right? So now we are taking the section between C and A. So our section is now somewhere between point C and point A, right? So if a section is between point C and A, so how much of the shear force is acting, right? So shear force at X now, which is beyond point C, is, now again it's RB, right? RB is what? RB, we have the value of RB as is WL by 2, right, minus W into X. Again the equations remains the same, right? There's no difference. Now at C, we have already seen at C the value is 0, right? So at point A, the value of X tends to L, right? And at X tends to L, shear force at A will be equal to how much? See, we have WL by 2 minus WL. So if we, to what we have? We have minus WL by 2. Now this minus sign tells us that we have the value of WL by 2 and it is acting downwards. Now if it is acting downwards, that means essentially that the SFD will be positive because we are looking at the right hand side of the X section that we have cut, right? Now, so we have got the values. Now we'll draw the SFD for this particular case. So let's draw the datum line. This is the datum line. Now at point B, we had WL by 2, which was down, and at A we have WL by 2, which was upwards. So this is WL by 2, this is WL by 2. One is positive, one is negative, and let's say this is point C. At point C we had seen that the value was 0, right? This goes something like this. So this is point C. At point C the value of the SFD was, shear force was 0 basically, right? So this is how the shear force diagram is drawn. Now let's go for the BMD for bending moment diagram. For BMD we'll take the let's take this X. So BM at X, right? So BM at X is equal to how much? It is, see, we have a force which is acting at half over here, right? Now for bending moment it is quite essential for us to draw this. So this is WL, just leave, let's say that we'll go with the RB. So RB was WL by 2 into X. Now this is with the negative sign. Why negative sign? Because it is anti-clockwise, right? So this is anti-clockwise. So minus WL by 2 into X, and plus what I have is I have W into X into X by 2. I don't know, this is the distance X, right? So W is the intensity, W multiplied by X, and it will act at half the point. So Wx into X by 2 is the moment, right? So I can rewrite it as Wx square by 2 minus WL 2 into X, right? So at point B, X is equal to 0. So we get that bending moment is equal to 0, right? Now at C, X is equal to L by 2, and so this was bending moment at B, and bending moment at C, X is L by 2. So let's put it up. So when we put that, we get W. So L square by 4 into 2, 8, minus W L square by 4, right? So if we open up this, we get minus WL square by 8, right? And if we go at point A, then we have X is equal to L. If X is equal to L, bending moment at A, if we put this in equation, so WL square by 2 minus WL square by 2, it's cancelled 0, right? So now how is the diagram for this particular case? What exactly is the diagram for this particular case? Now if you look very closely, you'll find out that the BMD will be positive because the effects of sagging, right? So we have, and should be a like this. So this is point C, and both the ends at end B and at A we have a value 0, and this over here will be WL square by 8. So this is the positive value. So this is the SFT of BMD for this particular case.